Hello, we are the Hobart Senior Design Team, and our project is to reduce the manganese content in solid steel welding wire. The members of our team include Anna Cole, Seth Eacker, Jack Schaller, and myself, Visscher. Our sponsor is Hobart, and our contact is Dr. Satya Kondapalli. Hobart manufactures welding supplies, and one of their main products is solid steel welding wire. Manganese is commonly added to the wire because it is a potent addition for strengthening welds and is also cost-effective. The reason manganese is effective at strengthening is because manganese lowers the eutectoid transformation temperature, which allows for more nucleation during cooling, resulting in a smaller grain size. Despite these advantages, manganese is a big health concern because during the welding process, manganese fumes are produced, and these inhaled fumes can cause brain damage similar to Parkinson's disease. Nickel is one possible substitute for manganese that our team has been exploring. It has a lower saturated vapor pressure than manganese in welding conditions. This means it will not vaporize in the welding process. However, nickel is 5 times more expensive than manganese, so we are trying to find the balance between health risks and cost. Similarly to manganese, nickel also lowers the eutectoid transformation temperature, which again promotes nucleation overgrowth of the ferrite during cooling. This leads to a finer grain size in the microstructure, which helps strengthen the alloy. Because of this, we propose that if nickel replaces removed manganese in solid steel welding wire, then the weld mechanical properties are maintained because nickel refines grain size. With this hypothesis, we were able to formulate a design of experiments. The design of experiments consists of 5 alloys, and the mechanical properties of these 5 alloys will be assessed and compared to the high manganese wire that Hobart currently produces and sells. Before any testing could happen, we first had to make our wire. This process started with casting and homogenization. Once homogenized, the bars were rod rolled and annealed as needed, and then swaged and annealed as needed. From there, most of the samples were sent to our sponsor for wire drawing, MIG welding, and testing, while a few of our samples were kept at MTU for further swaging, TIG welding, and testing. To start off, we needed to design a pattern for casting. This is so we could make 16-inch bars with a 3/4 inch cross-sectional side lengths. Inspire Cast, a casting simulation software, was used to ensure our bars would be free of porosity and cold shuts and would have proper cooling. The design pattern was then used to make Ken Bond sand molds. They were designed to make a total of 4 bars per mold. Once cast, the sprue cups and risers were removed and the bars were machined down. Multiple heat treatment methods were used throughout the process to ensure homogeneity and proper strain relief for processing. The homogenization time and temperature were determined using thermocalc simulation software based on diffusion rate of alloying elements. Annealing was used throughout rod rolling and swaging to relieve strain due to work hardening and prevent material failure. Rod rolling uses compressive force between 2 rollers to reduce the cross-sectional area of a sample. This process was used to bring our 16-inch bars with a cross-sectional side length of 5/8 down to a side length of 1/4, which resulted in approximately 8-foot-long bars. Like rod rolling, swaging also uses compressive force to reduce the cross-sectional area of a sample, but instead of rollers, it uses dies that open and close around the sample, resulting in a round cross-sectional area. Our bars were swaged down to a 1/4 inch diameter rod before some samples were shipped to our sponsor. The kept bars were further swaged to an 1/8 inch diameter. The 1/8 inch wire was welded into a V-notch between 2 steel plates and then machined into round tensile bars to test the elongation, ultimate tensile strength, and yield strength of our alloys. At this time, we are still waiting on the results of our project to determine which alloy will perform the best.